Welcome to Unit 3, Day 1, Exponential Functions. So an exponential function typically looks like this, the regular form, f of x equals a times b to the x, or we have something that is continuous growth or decay, something like that. To me, an exponential function is a repeated multiplication where you start at the value of a and you keep on multiplying it by b, x amount of times. A is the initial value. That's when I have x or t equal to 0. B is the change factor. How is it growing or decaying? And x is just the exponent of how many times it occurs. So let's look at some graphs. A exponential growth graph has to have b greater than 1. That means my multiplier is bigger than 1. I don't care if you multiply by 1.01, if something's going to grow. Or if I do the continuous one, it is when k is a positive value. E to the 0 is 1, so e to any positive value is going to be bigger than 1. So here's my graph. Always looks like this. I have this y-intercept here. I have this horizontal asymptote of y equals 0. And my domain is all real numbers. My range is only above the x-axis. It's only concave up the whole time. There is no symmetry. And as x goes to infinity, this graph goes up to infinity, and as x goes to negative infinity, it levels off to 0. So for exponential decay, is when b is less than 1. B can never be 0, it can't be negative, but it could be a decimal between 0 and 1. So if you multiply by some decimal between 0 and 1, things are getting smaller. Or when my k value for the continuous is a negative number, because e to a negative number will always be between 0 and 1. I have my x-intercept, or my y-intercept again. My HA is still the same. And basically everything else is the same. Domain and range, concave up. No symmetry. Except my end behavior is different because now the right end of x going to infinity is 0, and my left end of x going to negative infinity is going up to infinity. So let's look at the effects of the transformations of capital A, which is still the same A, the capital B, the capital C, and the capital D. The lowercase b is the change factor. And obviously, that is going to give me the steepness of the curve. When b is bigger than 1, it's going to grow. When b is between 0 and 1, it's going to decay. And this key factor right here, the closer b is to 1, the flatter the curve. So I'm going to compare some of these. What do I mean by flatter the curve? So it's easy to see on an exponential growth comparison that when the b value gets larger, the graph gets steeper. Or when the b value gets closer to 1, like this orange one, this orange graph is flatter than the rest. Now it's a little bit different when we do it for exponential decay. It's the same idea, but you have to think, what does it mean? So when we look at exponential decay graphs, the orange one is the flattest, even though the b value is the highest, because that b value is the closest to 1. Okay, we'll talk about it in a minute, but the idea is that the orange graph is decaying by 30%, the purple graph is decaying by 50%, and the blue graph is decaying by 70%. That's why the blue graph is the steepest. It has the greatest decay value, but the b value is and the b value is farthest from 1. As far as the other transformations go, the idea is A is just that initial value when we don't have any other transformations, but it does stretch or compress things. B is going to compress it horizontally or stretch or compress it horizontally. C will move it left or right. Remember, it's still this always, if we have two letters, negative C over B. And then finally, the D value, which is probably the most important, is this horizontal shifting up or down, and whatever my D value is, that becomes my horizontal asymptote. Okay, let's try some examples. I'm going to write the equation y equals a times b to the x. A is the initial value, or the y-intercept, and b is the change factor. Well, this one's nice. It gives me the a value for 100, so y equals 100 times b to the x. And then I could just choose some other point. 150 equals 100 times b to the first. 5 by 100. I get b equals 1.5. I get my equation. Y equals 100, 1.5 to the x. And if it's 1.5, it should be growing. And look, my y values are increasing. Again, I've given the a value. So y equals 50 times b to the x. I have another value I can use right here. 20 equals 50 times b to the fifth. I can divide by 50 and I get 0.4, 2 over 5 equal b to the fifth. And the only way to get rid of the fifth power is doing the fifth root or the 1/5. I get b is about this decimal 0.833, or y equals 50.833 raised to the x. B is smaller than 1 and the graph is decaying. Now it gets a little bit more difficult. I don't have my a value, so I have to set up a system. So I'm going to use this point first. 9 over 2 is equal to a times b to the second. Always put the higher x on top. And then the second part over 8/9 equals a times b to the negative 2. Because now I have a nice system here. I'm dividing them out. The a's do cancel. And I subtract exponents. I get b to the fourth. I do this math. I get 81 over 16, or some decimal like 5.0625. Okay? I take the fourth root of it all. I get b equals 3 over 2, or 1.5. So now I could do, I'm going to use this point here. I'd rather use a positive x value. So 9 over 2 is just 4.5 is equal to a. I still don't know a times, but I know b, 1.5, and the x value here is squared. I could just divide by 1.5 squared, or do it in the calculator. I get a is equal to 2. So my equation is y equals 2, 1.5 to the x. The b value is bigger than 1. It is a growth equation. Now we're going to look at problems that involve when we have percent increases or percent decreases because they're either growth or decay. I change my formula a little bit. I put this 1 plus r. 1 plus r because it's growing. R is the percent. I must change it to a decimal. In other words, 52% means 0.52. If I had something raising by 125%, that'd be 1.25, and so on and so forth. So look at this problem. This is 0.08. My population is 15,000. 1 plus 0.08 is 1.08 raised to the x, and I want to know what the population is 10 years from now. So I just put in the number 10, and I get 32,384. No decimals, for population. There's no such thing as 384.6 people. No decimals. So I have this reindeer population that's growing. D equals 29 reindeer. Growth 1 plus this. Raised to the x. I want to know how many I have in 1963. Well, the initial year was 1944, so I'm going to use x equals 19. So D equals 29, 1.324 raised to the 19th. And again, no decimals for population. I'm going to have a little bit more than 6,000 deer. And now I'm going to use my graphing calculator to figure this out. I'm going to put y1 is equal to my deer population. My y2 is equal to 1,000. I'm going to see where they intersect. Okay, here I am on my calculator. You can see I put in y1 and y2, the two equations. I'm going to find when they intersect. Now this is where I see most people have a problem with the graphing calculator. Picking a good window. I rarely ever hit graph unless I want to use the same window I just had. I'm not going to hit graph. I'm going to hit window. X, for this problem, for all exponential problems, the input X is going to stand for time, in this case number of years. The Y value is the output, or in this case the population of deer. So I could do 0 through 40 years. It's going to be less. I know in 19 years there were 6,000 deer, so I can actually do less. I can make it even less. I can make it 20 years, because in 19 years I had 6,000 deer. And I want 1,000 as my deer, so 600,000 is a little bit too much. I'm going to make it 2,000. And I hit graph, and I see there's the exponential growth, and there is my y equals 1,000 horizontal line. I got to find where they intersect. Second, trace, number 5. This one's easier. I just have to go enter, enter, and because there's only one point of intersection, I could just hit enter again. And there we go. I got 12.6 years. I'm going to go back to the worksheet and show you what we need to do. So the question asks, in what year? Well, the initial year was 1944, and it's 12.6 years later. So it's 1956. It might be July or August of 1956, but it's not the next year. When we talk calendar years, you have to be the whole next number. We don't round off like we do round off populations. Okay, exponential decay is very similar, except my equation has a 1 minus r in it. The 1 minus r is still the percent. I got to change to a decimal, so if it says decaying by 20%, that means I use 0.20, but it would be 1 minus 0.20, which is 0.80. So when you see that as your b value, that means it's 20% less than 100%, or 0.20 less than 1. So the Amazon rainforest is shrinking, we know. So my Amazon rainforest is 2.5 million. And let's see, I have to do 0.052, but I have to do 1 minus 0.052, which is 0.948 raised to the x. That's my general equation. When I want to do it for 8 years, A equals 2.5 million. 0.948 raised to the 8th, and I get 1,630,822.548 square miles, and I'm allowed to have decimals because this is square miles of rainforest. You could have decimals of square miles. Okay, for this next problem, oh, I already did it. Let me erase it. My initial amount, 16,000. Inside the parentheses, well, I have to do 1 minus 0.16, which is 0.84. And for 7 years later, y equals 16.84 raised to the 7th, and I get equals 4721.45, because I always use 2 decimals for money, always. So I need to identify either the growth or decay factor, which is the B value, and the growth or decay percent. So this one, my growth factor is 1.2, but my percent is 20%. This next one, my decay factor is 0.75 because it's less than 1, but my percent is 25% because it's 25 cents less than a dollar. This next one, my growth factor is 2.5 because it's bigger than 1, but my percent is 150%. And this last one, my decay factor is 0.912 because it's less than 1, and my percent is 8.8%. That's how we figure these things out. Now, another way to write equations is putting the amount of time frame into it. So when I use this formula here, the K is the amount of time to do a growth or decay. So when I see it's a half-life, my B value is a half. Originally I have 1,000 grams, so R equals 1,000 times a half, and since the half-life is 15 years, it's going to be T over 15. Because if I put in the number 15 here, if I put 15 in here, it would be 15 over 15, which would be 1, and that would be a half time raised to the first power, which is 1 half-life cycle. Okay? If I want to, oh, I'm sorry. I made a mistake. The half-life is 5 years. This is my bad. This is me not reading the problem. The half-life is 5 years, so it's T over 5. My bad. I'm not redoing videos. If I make mistakes, I make mistakes. You just have to watch the video. So again, this is my K value, this is my B value, this is my A value, and this is my equation. If I want to know for 15 years, I just plug in 15, I get half 15 over 5, and I do all that, and I plug this in the calculator. I have to do this part first. That's just 3. And I do this all, I get 125, and the units are grams. 15 years will equal 3 half-life cycles. Okay, thank you for watching the video.